Swayam Prabha. Digital India. Educated India.
So today's topic is sampling distribution part 2. The first distribution that we are going to discuss is known as T distribution. Now we would like to find out the distribution of means when standard deviations, that is sigma, is unknown. That is, we know the population, nature of the population, which is normal. Mean is also known to us, mean of the population, but what is unknown is the variance or the standard deviation of the populations. This was not discussed earlier. So this is what we are going to discuss now, that when we have no idea about the population standard deviation or variance, then if we keep drawing samples from this kind of population where the population standard deviation is not known, then how the sample means will be distributed. Now, when the population standard deviation is unknown to us, then we have to use the sample standard deviation as an estimate of population standard deviation, provided, this is very important, that n is very large. That is, we make sure that the sample size is large. So large basically means it should be at least 29, 30 or more. So when the value of n is large, then we can say whatever is the estimate of sample standard deviation, that will be, or whatever is the standard deviation of the sample, that is going to be the estimate or a good estimate of the population standard deviation. So we all know what is the formula to calculate sample standard deviation. This is a very well-known formula, and most of you would know this formula by now. So this is the formula which is used to find out the standard deviations of the sample. Now, if the standard deviation of the sample, once it is known, then the variable t, what is this variable? Xi bar minus mu by s over root n. This variable follows a distribution known as T distribution with parameter nu, and nu has a degree of freedom n minus 1. Nu is known as degree of freedom. So the value of nu is going to be n minus 1. And T distribution, how does it look like? That is what is shown in this particular diagram. It is quite symmetrical in nature, and the T distribution, the shape of the distribution changes as the value of nu is going to change. So nu 1, nu 2, nu 5, nu infinity, the distribution has been plotted, and you see this distribution is also quite symmetrical in nature, and when nu is infinity, T distribution becomes exactly equal to normal distributions. So nu infinity basically means nu is more than 29. That is, if we take sample size which is 30 or more, then we can say my nu is very high, and therefore it is close to the distribution that you would expect will be very close to normal distribution. If the value of nu is less than that, suppose it is 10 or 12 or 7 or 8, then the distribution is going to be t distributions. So when nu value is high, we may not consult t distribution table. We can directly consult the standard normal distribution table. Otherwise, we will generally consult the t distribution. Mean of t distribution is going to be 0, which is shown here. And the variance depends upon the degree of freedom. Variance is greater than 1, but it tends to 1 as n tends to infinity. And when the sample size is large, the variance will be close to 1. That means it is going to be very close to standard normal distribution. You will be remembering that for standard normal distribution, that is we call the distribution of the variable z. For that, the mean was 0 and the standard deviation was 1. So when the sample size is large, t distribution will approach standard normal distribution. And since it is approaching standard normal distribution, therefore the value of the variance is going to be almost 1. Like Z table that we have seen earlier, we have discussed earlier, we also have T tables. So on the right hand side, we have data related to T tables. For various values of alpha, the alpha is the area of the curve on the right hand side of the T variable. So in this case, this axis is basically T. For standard normal distribution, this was Z. So Z is get replaced by T. Everything remains same. The understanding is basically exactly same. So in this case, the T values for different degrees of freedom has been quoted in this table, in the columns that you see, for different values of alpha. So here is a value of alpha which is 0.05. Then we have value which is 0.025, then 0.01. So what alpha indicates? Alpha indicates the area of the curve on the right hand side of the variable t, which is shown here by the shaded area. So the way you use the table is exactly similar to the way we use the Z table earlier. There is no difference. So T table gives the values of T alpha for various values of nu. Nu is the degree of freedom, where T alpha is such that the area under the T distribution to its right is going to be alpha. So this is where alpha is shown. It is not necessary to tabulate values of T alpha greater than 0.5, since for symmetry of T distribution is also very symmetrical. So if we get the table for the right half, we can use the same table to calculate the values of T if we go for the left half. That is when you get T values which are negative, less than 0. So 0 is here. So all this side, right hand side, T values will be all positive. On the left hand side, if we go this side, the T value that you get here on this, they will be all negative. Therefore, T 1 minus alpha is going to be equal to minus T alpha. Now here, how to read this table? For suppose the degree of freedom nu is 14, and alpha is 0.01. Suppose these two values are known. So what is the corresponding t value? So alpha is the area on the right hand side of t is given, that is 0.01. So we have to see in this column which column is for 0.01. This is the column which is 0.01. So this is the column where we have to now focus. And now we have to find out that where new value is 14. If we go down this column, we find here is 14. So we will go in this direction, and where we should go, where this line and along this line they are matching, they are crossing each other. So that is the point. Here whatever value we get, this value is actually 2.62. Therefore T alpha is 0.01 and nu 14, the value of T alpha is going to be 2.62. This is how we have to read the table. So in a way, this T table or reading T table is similar to the Z table that you have already studied. So there are a lot of similarities are there in the calculation part also. Instead of calculating Z, we will calculate T value here. Rest remains exactly same. And instead of consulting Z table, we will consult T table in this case. Why? Because the variance or standard deviation of the population is unknown to us. So wherever such kind of situation will arise, where we have no idea about the variability part, then we have to go for T distributions. Now we will take an example to understand it further. So let us read a numerical problem which is here. A fuse manufacturer claims that with 20% overload, the fuses will blow in 12.4 minutes. You all know about the fuse. You use fuse in the domestic, electrical boxes. We have all, and many electrical appliances are there where fuses are used. The purpose of the fuse is to protect the equipment. That's why you use fuse, so that when the current goes up, the fuse will get fused and there will be disconnection. The supply will be disrupted and the equipment will be protected. That is why fuses are used. Anyway, so the manufacturer claimed that with 20% overload, the fuses will blow in 12.4 minutes on an average. To test this claim, a random sample of 20 fuses was subject to 20% overload. The mean blowing time is found to be 10.63 minutes with standard deviation 2.4. So the mean is given and the standard deviation of the sample is also given. The data is assumed to be part of normal population. So nature of the population is also stated. Now the question is, does it support the manufacturer's claim? Manufacturer's claim is, on an average, the fuses will blow in 12.4 minutes. That's what is the claim. However, by doing test on 20 fuses, we get a mean value of 10.63, which is less than 12.4. The standard deviation was 2.48 minutes. Now, does it support the manufacturer's claim or not? So we do a test. And what test we should do? It is T test. Why I am doing two tests? because we do not know the standard deviations of the population. So you see, nowhere it is written what is the standard deviation, what is the variance of the population. This is not known to us. Therefore, we cannot perform Z test. So the alternative is we have to go for T test. So we'll calculate T. So calculated T, we write T cal. In short form, I have written, this means T calculated based on the data that has been provided. So it is sample mean minus population mean divided by sample standard deviation by root over n. This is the formula to find out the value of T. So we substitute the values, all the values are stated here. So what is important, you to remember this formula. And this formula and the formula for Z are also exactly similar. The only difference is S will get replaced by sigma in the case of normal distributions. Rest is exactly same. And if we substitute the values, we get a figure minus 3.21. That is the value of T which we find out by doing the calculations. So we call T calculated. Okay. Now the next step. What is the degree of freedom? This degree of freedom concept does not arise in the case of Z. Only in the case of Z test. It only appears in the case of T test. So degree of freedom here will be how much? The n value was 20. 20 minus 1, therefore it is 19. The probability that T will exceed 0.05 let us see the table this side, that T will exceed 0.005, let us say first of all. Here it is 0.005, and similarly what we have to go, we have to find out for 0.005 what should be the value of T given in the table. So the table value of T has to be compared with the calculated value of T. Which one is greater, that we need to know. So we first try to find out for alpha 0.005 what is the value of T. For degrees of freedom, how much? 19. So if we go there 19, we don't find 19. We get 18 and 20, but 19 is missing in this particular table. In some other book, you may get a T distribution table where 19 may appear. Here, because to make the table little shorter, some values of degrees of freedom, they have been omitted in this particular table. But if we consult some other book, you may find that T19 exists there. So we take 2.88 and 2.85, sum them up and then divided by 2. We get a figure 2.865. That is what the value of T that we get from the table. So this value and the calculated value, if we compare, the calculated value is less than 2.865. It is negative, that means we have to actually we're going this side. Where it is, about it here it is minus 3.21. and here it is minus 2.865. So this is less than this. And therefore, conclusion is the data tends to refute manufacturer's claim, and we will say the mean blowing time is less than 12.40 minutes. So the claim is therefore rejected. Statistically, it is rejected, and we are pretty sure in rejecting the claim. The next distribution that is of importance to us is chi-square distributions. Now, what is chi-square distribution? We are going to discuss now, and where this chi-square distribution is going to be used. You will find the use of chi-square distribution in many situations. So first we need to know what is chi-square distributions. Let Z1, Z2, Z3, Zk are chosen at random from standard normal distribution. So standard normal distribution, you know that the variable Z follows standard normal distribution with mean equal to 0 and standard deviation equal to 1. And let us say we randomly picking up the values of Z, Z1, Z2, Z3, Z up to Zk. And then we write a function chi-squared k, which are sum of Z1 squared, Z2 squared, Z3 squared up to Zk squared. So this is the summation of square of standard normal variable Z. If we add them together, then we get a value chi-squared k. Now if this is repeated number of times, then chi-square values will be generated which may have a distribution. We will get various chi-square values. So we first take k numbers of Z values randomly, square them up, and then add them together. We get some values of chi-square. Suppose that is chi-square 1. Again we go for finding out chi-square 2. So in chi-square 2, we again take Z values, which is Z1, Z2, Z3, Z4 up to Zk. Then we square them up and add them together. Then we get chi-square 1, chi-square 2, chi-square 3, chi-square 4. We keep repeating this. And if we repeat it suppose 30-40 times, then we will find that there are various values of chi-squares, and therefore it also follows a distribution. It is known as distribution of chi-square. The sum of the squares of normalized variable z's follows the distribution which is chi-square. The name is given chi-square with k degree of freedom. K is the number of z variables that we are choosing. And degrees of freedom is how much? K equal to n minus 1. Now some chi-square graphs are shown here. What we see here, the chi-square distribution is skewed. So you see all the graphs, the blue, the orange and the green. All has chi-square graphs for different values of degrees of freedom. df equal to 4. Here the blue one is with degree of freedom 4. The degree of freedom 8 for the orange one, the degree of freedom 12 for the green one. So if we see that the skewness is decreasing as degree of freedom is increased. So as degree of freedom increases, the chi-square distribution becomes more and more symmetric. The mean is k for chi-square distribution and the variance is 2k. This can be, we need not to prove it, let us accept it that the mean of chi-square distribution is k and variance is 2K. And similarly, like Z table, T table, we have chi-square table also. So chi-square table also quotes the values of chi-square for a given value of alpha, where alpha indicates the area on the right hand side of chi-square value, as it is shown in the diagram. So chi-square table gives the values of chi-square k alpha such that the area in the right hand side tail beyond chi-square k alpha, this is beyond this point is chi-square k alpha. So this is what is actually alpha. So this area shown by this pink is the area of the chi-square distribution curve, or this is the, you can say, the probability. So for different values of alpha, the chi-square values have been quoted. So there is some for certain value of alpha, the chi-square value here, whatever is the chi-square value, that will be given in the table. Then if I keep changing the value of alpha, we'll get different values of chi-square. So that sort of table is already there, like we are showing you a typical table. Here the alpha values are here, and this is the degree of freedom. K values are here. So this column is about, first column is about degrees of freedom, and the rest of the columns are the values of chi-square for different values of alpha. This is 0.995, this is 0.975, alpha values here 0.95, here the alpha is 0.05, 0.025, 0.005. These are the different values of alpha or different areas. So for a given k, suppose when k is 1, then these are the different values of alpha. So this kind of table will be available in many textbooks, and you need to consult them to find out what is the value of chi-square for a given value of alpha. When, say, if I take one particular, let us say as an example, let us take a value of k5, and if we go along this row, when we reach the last column, the value is 16.75. So that means when the area beyond this chi-square values, the alpha value is how much? 0.005. So if I draw it again here, when alpha is only 0.005, so alpha is somewhere here. This chi-square value will be very high. So it is therefore 16.75. These are chi-square value. And if I go to, let us say, 0.05, 0.05 will be somewhere here. So that time the value, how much it is given, it will be obviously less, because chi-square value starts from this side, where at this end it is 0, and then it keeps on increasing. So this value will be less than this value. So if you look, compare, it is 12.83 here. It is less. So when the area under the curve is going to be, let us say, 0.995, that means this whole area is 0.995. In that case, this value, chi-square value here will be how much? What is quoted here? 0.412. So as we increase the alpha value, the chi-square value will decrease. So therefore, the values quoted under 0.005, they are maximum, and the values quoted under 0.995, they are minimum. So this is how you'll be able to understand actually what the curve is going to represent at what information it is giving to us. From there, this chi-square distribution is going to help us now in trying to find out the sampling distribution of sample variance. See, earlier we have discussed about what? Sampling distribution of sample means. We have not discussed about the variance, but many a times variance will be equally important to us. We need to know whether the variability has reduced or not. Suppose there is a process, we are manufacturing something, maybe a yarn we are manufacturing, or a filament we are manufacturing, or it could be a fabric that I am manufacturing, and there is too much of variation in some property. Whatever is the property, you can think. It could be strength, it could be elongation, it could be modulus, it could be breaking energy, it could be anything, any property. Suppose the variation is too much, too high. So we make some changes in the process. So some process parameter is changed, and then again we want to check whether there is a reduction in variability, or there is an increase in variability, or the variability has not changed at all. These three questions come to our mind when we make some changes in the process. So therefore, we need to compare the variability. We are not that time interested about the mean. Mean may remain same, but there is too much of variability in the property, and therefore the fabrics are getting rejected. The customer is rejecting the fabric because there's too much variation in maybe GSM of the fabric. So we need to then bring it down. So therefore we need some corrective action in the process. And hence our focus is to check only the variability aspect, not the mean. So sampling distribution of sample variance for random samples from normal populations. Population is normal. Since variances cannot be negative, it cannot be a normal curve. A normal curve, a standard normal curve, will have a negative value or positive value. It is symmetric. But variances can never have a negative value, which is always a square. Let the population be normal and standard deviation be, let us say, sigma of the population. A square is the variance of the random sample of size n taken from the normal populations. Okay. If it is so, we can say that this particular ratio n-1 a squared by sigma squared, this ratio has a chi-square distribution with k n-1, with k degree of freedom is n-1. This can be stated. n-1 into a squared by sigma squared, that is going to follow chi-square distributions. And chi-square alpha is the area under chi-square distribution to its right equals to alpha. That we have already discussed earlier while discussing the chi-square distribution. So the ratio of variance a squared by sigma squared, but then multiplied by n-1. This whole thing follows chi-square distributions. So that gives us a way to compare whether there is a change in the variability or not. Now, why it follows the chi-square distribution, that proof also is given here. We know the a square formula is this. Here I think the sigma will come on the top. S square is, if we write, it is sigma xi minus x bar whole square divided by n minus 1. That is what is a square. This is what is a square. So n minus 1 into a square equal to sigma xi minus x bar whole square. Now we divide both sides by sigma, that is population standard deviations. So we write n minus 1 a square by sigma square is equal to x minus x whole square by sigma square. That is whatever we have here, we can write this sigma should come there at the numerator, and therefore it's a summation of sigma xi minus x bar whole square. So we can write this plus this for different values of I. I is going from 1 to k. This variable was not told to you earlier, or you have already learned that z, there's a variable called z which is x minus mu by sigma, which is known as standard normal variable. If we compare this with this, we see that mu is not there. Otherwise, it is xi minus x1 minus x bar by sigma. That means there is a difference from the sample means only. But this z variable is x minus mu. Mu is the population mean. So population mean is not appearing, and in this case they are replaced by basically by sample means. So in the right hand side of the equation, the population mean has been replaced by x bar. Hence the right hand side terms can be regarded as sum of square of standard normal variable z, because x bar is a good estimate of mu. Therefore, for all practical purposes, we can assume that x bars are basically mu. And if it is so, then all of them becomes what? This will become then my z1. Z1 square. This will become z2 square, and this will become my zk square. And therefore, the sum of this standard normal variable z1 square plus z2 square plus up to zk square, this sum is known as, this follows chi-square distribution. Therefore, if the right hand side follows chi-square distribution, that means this is going to follow chi-square distribution. N minus 1 a square by sigma square is going to follow chi-square distribution. So that is what, how the proof is, that y n minus 1 into a square by sigma square follows chi-square distribution. So this ratio follows chi-square distributions, and we can compare the variability by using this particular ratio n minus 1 a square by sigma square, because we know this is going to follow chi-square distributions. Now we will solve a problem to understand it better. The variance of a normal population is given, that is 21.3. This is given already. This is the variance. Now it is decided that this claim will be rejected if the variance of a random sample of size 15 exceeds 39.74. What is the probability that a claim will be rejected even though sigma squared is 21.3? That there is some understanding between the, suppose the customer and the producer, that if the customer chooses 15 samples samples of size 15, and then he measures the variability. And it is decided that if it is more than 39.74, then the claim will be rejected. That it will be considered that the variability is more. So what is this probability? Solution is sigma squared is given, a squared is given, value of n is given. K value is 15 minus 1 equal to 14. Chi-square value we calculate. This is the formula, and we get a figure, chi-square figure 26.12. So this is the calculated value of chi-square. Now from the table we have to find out what is the chi-square value when K value, degrees of freedom, is 14, and let us say we choose a alpha value 0.025. And then we have to look at our chi-square distribution table, where chi-square values have been quoted for different values of K. And if we try to find it out, what values of 26.12 at K equal to 14 is here, and the chi-square value 26.12, if we go along this row, we come here and get a figure 26.12. And for this figure, we try to find out what is the corresponding value of alpha. So we go this way first, get the figure 26.12 which we have found out, and then we find out what is the corresponding value for alpha, 0.025. So probability that this will be 39.74 is going to be 0.025. So this area is going to be 0.025. Now come sampling distribution of the ratio of variances. This is another. In the previous case, the variance of the population was known, which was sigma was known. Now sometimes we want to compare between two samples, and we want to compare the ratio of their variances. Now F distribution is a distribution which will be helpful in this case. Now what is the F distribution? This is ratio of variances of two independent random variable. That is, it follows a distribution which is called F distribution. This is needed when we want to know whether the samples coming from populations have equal variances or not, or there is too much of difference between the variances. That time this kind of situation may appear, and we need to get an answer. If they do, the two sample variances will be nearly equal. And the ratio will be close to 1. If the variances are very close to each other, then their ratio will be close to 1. Otherwise, the ratio is going to be more. Now, the situation is that the population is normal and the variances are not equal. That means in this case, there are two populations are there, two separate populations, both are normal and the variances are not equal. So one population has a variance sigma 1 square, another population has a variance sigma 2 square. So two separate populations. Maybe two batches of cotton cones are there. And we are interested to know the variability of their count variation in them. It may happen that I buy some cheeses from mill A, I buy some cheeses from mill B, because I have two different suppliers. And both the suppliers are giving me same count of yarn, and we are then trying to use them, and maybe we are making fabrics out of it, maybe knitted fabrics or maybe woven fabrics, whatever it is. So there are two suppliers, and what we find that the variances are not equal, they are different. And if we draw samples from these two normal populations, sample 1 shows a variance of S1 and sample size is N1. Then for another population, it is S2 square and sample size is N2. Then F, which is the ratio as shown it here, S1 square by sigma 1 square and S2 square by sigma square. This ratio follows distribution which is known as F distribution and which is shown here, how it will look like. This F is a random variable having F distributions, this ratio with parameter nu1, this degrees of freedom. Sometimes we express it by K1 or nu1. So we can write in this diagram, it is shown as K1, K2. So we can make it K1 and K2 instead of nu1 and nu2. So you will find that sometimes they are expressed by the symbol nu or sometimes by K1, K2 or nu1, nu2. Anything we can use it. But because this diagram here I find it is K1, K2, so I change the nu1 and nu2 to K1 and K2. And they are degrees of freedom. So it is N1 minus 1, this is N2 minus 1. And the curve will look like this. It starts from 0 and then it goes like this. The other case could be when the variance are equal, populations are normal, the variance are equal, then actually what happens, the F becomes simply the ratio of variance of individual samples, because if both are same, then S1 squared by sigma squared, S2 squared by sigma squared, if we do, then sigma squared will cancel, will be left out with S1 squared by S2 squared. So ratio of sample variance follows F distribution. Rest of the things remain same, that is K1, K2, they are degrees of freedom, and the curve will look like this. It will be starting from 0 and go towards this side will go up to infinity. And this is the area. And similarly, for a given value of alpha, we can find out what is the corresponding value of, for a given alpha and K1, K2, that is degrees of freedom, we will know what is the corresponding value of F. So what is the value of F here? When alpha is given and K1, K2 is also given. Here we are a problem we are solving now. If two independent random samples of size n1 equal to 7 and n2 13 are taken from a normal population, what is the probability that the variance of the first sample will be at least 3 times as large as that of the second sample? That means, so what is the value of f? It will be 3 times larger than the other. So f1 by f2 or s1 square by s2 square should be greater than or equal to 3. For nu1 equal to 6 and nu2 equal to 12, we find out from this F table. The graph is shown, and here see nu1 values are quoted here 1, 2, 3, 4, 5, 6, and nu2 values are there along this column. So for 6 and 12, I have to come where 6 is here. This is the 6, and 12 is not shown in this particular table. It will be 10 is given and 15 is given. So if I know the value of 10 and 15, then we have to then extrapolate to find out what is the value of, what should be the value of f. So we consulted another book where the detailed table is given, and there it was found out that for f equal to 16, 12, these two are degrees of freedom, the 6 and 12. For area, which is 0.05, it is actually 3. Therefore, the probability that it will be 3 times as large as of the second sample is going to be 0.05, because this value will get when alpha value is actually 0.05. So you have to keep checking. This table is given for alpha equal to 0.05. Similarly, you can get another table where alpha value is given 0.01 or 0.025, because for different alpha values there is a table available. So now we need to know that this figure of 3, in which combination of nu1 and nu2 we get. So if we consult this table, then here we get a figure which is close to 3, and therefore we will say this probability that this will be 3 times larger is going to be 0.05, because in this particular table this value is available. If we go to the other table quoted for 0.01, you may not find this value at all. So you have to discard that particular probability. So for one value of alpha, or this value of alpha, for different combinations, the F values are quoted here. So if we go to another value of alpha, this is suppose for alpha equal to 0.05. If I go for another value of alpha, 0.01, so that will be somewhere here. For that, another table we need. In one table, we cannot accommodate everything. For different each values of alpha, we require a separate table now. It's the same table shown. The scale is larger so that visibility is better. There is another example is given here. 2 samples are drawn from independent, normally distributed population A and B. Population A, N1 is 16 and variance is 47.3. Population B, N2 is 13 and S2 square, that is variance, is 36.4. At the 0.05 level of significance, is there evidence of difference between the variances? Can we really say that there is a difference in the variances. One variance is 47.3, the other variance is 36.4. In one case, we have taken 16. Sample size is 16. The other case, sample size is 13. Now we want to compare their variability. So, how to go about it? Solution is calculate the values of F. We take the value whichever is larger. S1 squared is larger, so 47.3 by 36.2. If the other it happens that S2 is larger, then S2 will take, we consider S2 as S1 in that case. And now this value is this. If we consult the table for F with degrees of freedom 15, why 15? Because 16 minus 1 makes it 15, then 13 minus 1 makes it 12, and level of significance given 0.05. For that, the corresponding value is 3.18. Now this value, F calculated value, is much less than this. So the evidence is not really strong that there is a difference in the variances. So this is how the problem solutions are only 3-4 lines. They are not really lengthy problems. It is only 3-4 lines. You need to know how to read the table and what values you need to find out from the table, and how to compare that value with the calculated value. And then based on these two readings, calculated value of F and the table value of F, we can say whatever you see from table, we can say this table value of F. We compare and then make our own conclusions. Okay, so with that, we come to the end of this particular topic related to the distribution of samples or sampling distributions. So we have discussed sampling distribution of means first, then we have discussed sampling distributions of variances. That also we have discussed. And we have seen what is chi-square distributions and when to use chi-square distributions. We'll also find that there are other situations will come, we'll discuss about them, where chi-square distribution can be used. And what is F distributions also, that we have come to know. So all these distributions are really important for taking decisions in a industrial situations also, because many a times we have to change the parameters and see what is happening to the property of the fabric or property of the yarn, or for that matter anything that we are making, and we need to check, and by applying the statistical techniques or tests, we'll be able to confidently say whether there is a change or not. We'll learn more about them in the coming lectures also. So with that, we conclude today's session. Thank you.